I'm absolutely delighted to be here. It's always nice to be at the Indaba. It's always nice to also have an opportunity to participate like this. So thanks for coming to the tutorial. And the whole point of the tutorial, as you know, there'll be practical sessions later. And this tutorial is really to just build some intuition. So what I'm hoping to do with this session is to not focus like too much on specifics. There might be some aspects that are glossed over, but really the objective is to just build intuition. Like, what is reinforcement learning about? What is this policy gradient approach about? And just to get some sense of what's going on. And then there's the opportunity in the practical to have a bit of like a deeper dive. I also would appreciate if it's like quite interactive. So even though it's more like talk style, there's no notebook to follow along. I will be going through a notebook with some examples and things, and just to build some extra intuition and make it easier to understand. So first of all, just why to care about reinforcement learning in the first place. Those who have never heard of it before, it's sort of like, you know, this approach to AI that's really built from trial and error, learning, same as what happens in sort of the natural world. And it's had some really big successes. So since 2021, with general systems that can play games to superhuman level, all the way up to today's reasoning systems such as Gemini Deep Think and achieving things like gold medal in the International Math Olympiad. So of course there's other things under the hood with these systems, but they heavily also rely on reinforcement learning. In fact, this is the quote from the blog post saying that to make the most of the reasoning capabilities of Deep Think, we trained the version of Gemini on novel reinforcement learning techniques. So it is an approach, it is a technology that is really sort of coming to the forefront and is in sort of everyday life now. Maybe a few years back, reinforcement learning didn't make its way all the way to sort of applied products and things like this, but it's very much commonplace now. Okay, so to build some intuition, we are going to make things very, very simple. There is this robot. His name is Steve, and he's in this world. That's this number line. So Steve is at the leftmost side, where it's 0. We have these discretized points leading all the way to the number 1. And Steve, the robot, needs to get from basically left to right, to go from 0 to 1. That is the only thing Steve cares about. And we're going to try and help Steve, the robot, achieve this. So everything we're going to do now is really with this goal in mind. And my objective here is to really give you as much as I can in terms of the intuitions behind reinforcement learning, also the intuitions behind the policy gradient method, which is an approach to solving reinforcement learning problems, just through this very simple case of a discretized number line. Okay, to do that, we're actually just going to hop over to a notebook. So I'm going to make this bigger. Can people see this? It's fine? Okay. Okay. So the first thing we're going to do is we're just going to create a very simple number line. Okay. So this is what it's going to look like. Instead of the other sort of slide you saw, we're going to make it even simpler. So there are just 4 dots here. We're starting on the left with the blue dot. And everywhere the blue dot is kind of representing where Steve is in this number line world. So he's starting on the very left point. And Steve's goal is to get all the way to the right. Very simple, okay? There are a few things here, a few like sort of in reinforcement learning nomenclature, if you will. These positions Steve can be in, we call them states. So every dot here is a different state that Steve can be in. The number line itself is the environment Steve is in. So in this environment, there are 4 states. There are actions. Steve can take particular actions. He can go left or he can go right. In some states, this will have sort of different dynamics. So for example, if in the very first state, Steve decides to go left, he will actually just stay in that state because there is nothing to the left. So there are certain dynamics that govern this environment as Steve takes actions in a particular state. So that summarizes just this very small world that Steve is in. Now, what do we want to do? We want to have Steve come up with some strategy, some way of moving from left to right. Super simple, right? Like, if we look at this, it's quite obvious what Steve should do, but imagine Steve has no idea what he should do. So how do we get Steve to do what he needs to do? This brings us to the concept of a policy. So a policy is basically sort of like a recipe or a strategy, as you will, to, given you are in a particular state, given Steve is somewhere on this number line, what should Steve do? What should he decide to do in terms of the actions he should take? So Steve can move left or he can move right. And so everywhere along this number line, he can decide, given he is somewhere along the number line, to move left or to move right. And the whole sort of goal here is to get the best policy we can. Okay. So now we are just going to create a policy. We're just going to create, sample sort of a random policy here. Okay. So let me explain. You see 4 numbers there. There's this array. Each index in this array represents the state Steve can be in. And the number represents the action that Steve can take. 1 being moved to the right, -1 being moved to the left. Okay? So who can sort of give a guess as to what this policy would do if Steve started in the leftmost state and he followed this policy, this strategy for taking actions? What would happen?
Yeah.
Yes. I mean, at the beginning, you say that when the robots are not able to go to the right, stay at the same place. So how do you formalize that in this array? Because right now it's like right, left, left, right.
Yes, sorry, to clarify, what I meant is if Steve's at the starting state and he decides to go left, there is no state to the left, so he'll stay at the starting state. But if he chooses to go right, he will move to the right, but there's also the dynamics of the environment, which might have an influence, yeah.
No, let's say, let's say he's at 1, right? And he's at the beginning, so he want to go right.
Yes.
Okay? So he realized that he don't have 1 to go to the right. And he don't go to the left because it's not his purpose. So how do you formalize that? The fact that at t and t plus 1, he's at the same place. Because there is time, right?
Yes. So every time Steve is in a particular state, he can choose an action. And when he chooses an action, then the dynamics of the environment will take over and do a transition. So if Steve decides to move right, then this environment essentially reacts to Steve's decision to move right. So underneath the environment, the dynamics could be completely known or not known. And here, I'll say a little bit more about the dynamics later, but it's pretty straightforward in the sense that if you move right, you will likely move right. Yeah.
4. So in this case, it'll move to the right 1 step at the end of all 4?
Yes, so in the first state, the starting state, there's a number 1, so that means Steve will move right, and he's in the next state. Then what will happen? What's Steve's recipe then?
Then he'll move left, but the next left he can't move, and then he'll move right. So
Yes.
he'll be at 1 step from 1 step to the right from the beginning state.
So what would this look like if you just had Steve do, 10 steps. If he followed, if he would always, let's ignore the dynamics now and say it's completely fixed. If Steve moves right, he'll always move right. There's no funny business there. If he moves left, he'll always move left. What will happen with this policy?
He'll move one step to the right every time he does this.
But when he's in state 1, what happens? He moves?
He moves back to the same place, so it just remains at state 1, stuck.
Yes. So let's see. Let's see what happens here. So this is Steve, and he's now following this policy. Okay? So again, let me recap. These 4 numbers represent the state. The values in them represent the action Steve's going to take. He starts in this leftmost state, and 1 means going to the right. If he's in the next state, it means he's going to take the action to go left. If he finds himself in the 3rd state, he will choose to go left. If he found himself in the last state, he will choose to go right. Okay. So here, what we'll see is the following. Steve's just bouncing around. So Steve's not reaching his goal with this particular recipe, with this particular policy. So now the objective for us is to get Steve to do the right thing. Okay. So what do we do with RL? What is the whole point? And like we said, it is to find this policy which we deem to be the optimal policy. We want to find the best recipe, okay? And how we can do this is we can encode in the environment certain things that will kind of give a signal for good behavior. And then if this signal is a good signal and it can be optimized for, then we can use this to get better and better policies. So one way we can give Steve some signal as to what is the right thing to do is to say that if he reaches the end goal, if he reaches the right side of this number line, he will get a reward. And this reward is just going to be a number. We're going to give Steve a number of 1 if he reaches the goal of being on the rightmost side. Otherwise, we're going to give Steve a 0 everywhere else that he finds himself. So in some sense, if Steve's only goal is to get positive reward to push the value up, then Steve must go to the most right side of this number line. This is sort of how we are incentivizing Steve. And then there's some extra things we're taking into account here. What is an episode? So an episode is just something that in the RL literature or the world of RL is referred to as the period of time where Steve would particularly start in his state and then move steps continually until he either reaches his goal or there's some termination condition. And what we want to do is we want to find a single quantity, there's a single number that quantifies how good is an episode. If Steve were to take a policy, his recipe for acting in the world, and he would act in this world accordingly, we want to summarize how good was that. And with that, we can do with return. So return is simply just this sum of rewards that Steve is getting during his episode. But there's one extra ingredient here. We are discounting this sum. We are essentially discounting future reward values from where Steve is beginning. So if Steve is in the starting state, he'll move to a next state by taking a certain action. Steve will receive a reward from visiting that state, and so on, as the policy rolls out and the environment dynamics rolls out. And from the very first state, if you were to sum up all the rewards, you would get the return. Why do discounting at all? If we if we have a reward at the very end of 1 to finish the going from all the way left to the right of the number line, and 0 everywhere else, why might it be a good thing to discount the future rewards from the starting state? And just to be clear, what I mean by the discount is there's this sum at each state where Steve finds himself. He could get a particular reward, and then as Steve is moving to the next state from state 0, he could get a second reward, but now this reward is reduced by some discount factor that's less than 1. So something like 0.98 or, yeah.
Is it perhaps because you want Steve to get to the solution quicker?
Exactly. So if you think of like this discounted sum from the starting state, the longer Steve takes to get to the end goal to receive a reward of 1, the higher the discount factor is going to be for that actual reward 1 eventually when he gets it, as calculated from the starting state. So if we didn't do this, Steve wouldn't try to find a policy that's really just, getting to the end as quickly as possible. So the gamma value can be, it can be 1 with no discounting. That just means that there's no preference in terms of immediate reward versus rewards gathered in the future. So here, if we set the gamma value to 1, we won't necessarily see that effect that it's better to have policies that try to have almost like the shortest path to the end goal. But any value smaller than 1 is kind of a stricter penalty on how long it takes to get there. Yeah.
So if I may ask, so if the reward is only allocated for the goal state, wouldn't the other R's in between before getting to the R state be equal to 0?
Exactly, yeah. So all these, all the rewards gathered before transitioning to the goal state is just 0. So imagine this discounted sum. Basically, let's say this RT is the reward of finally reaching the goal state. So it's going to have a number that's equal to 1. Everything else is going to have a 0. So everything else cancels out. But this factor here, this exponent, is basically growing the longer Steve is not reaching the goal state. Okay. So what is some strategies for us to find a better policy? What can we do to get Steve to do the right thing? Well, one approach is called sort of just random policy search. So what does this look like? It's basically we sample a policy. So if we sample 4 numbers, essentially, and with each number is either a 1 or a -1 in terms of moving right or left. We run an episode to see what that policy does for us. We calculate the return from the starting state, which is a summary of basically how good was this policy when we executed it in the environment. How good did Steve do when we gave him this recipe of what actions to take in what state? And then we essentially just say, okay, if the return is better than the previous policy we tried, we keep that as the best policy, because that's the best policy so far. It's getting the highest return. And we repeat. So we just randomly sample, see what Steve does, say, hey, here's a random recipe, try this recipe, go do it in the environment, see how well it does. If it's better than the previous one, this is the best one so far. Okay. So you don't have to focus too much on the code at all. We're going to run this idea and see what happens. Okay. So here, let me just zoom. Okay. Hopefully everyone can still see this. So this is what happened. We did a few episodes. We computed the return. And we have these jaggedy spikes. This is in parallel, by the way. So one thing is to do it sequentially. Here what we're showing is parallel samples of policies. We rolled them out, each one for their episode, and now we're just plotting for the 100 episodes that we did this, what's the return that we got. So I don't know if someone would try and interpret this graph for us. So on the x-axis we have episodes, the y-axis total return. If you had to find a good policy here, what would you do?
You will look at the number 1 at the top. So let's say the first episode is around 20, less than 20, but you reach at the top at 19, and so on.
Exactly. So in the sampling process, where we sampled 100 times and ran 100 episodes, we found a few winners. We found a few policies that actually got a good return. So we can now check and just find, the policies at that specific index and pull them out and say, okay, well, this is the policy we should use. What's going on here? Why is there this slight dip between these two? So most of them seems to get sort of a return just below 1, but they're not all exactly equal. There seems to be some sort of shared optimal policy, but there's slight differences between them.
I think this is because we have this discount factor that penalizes state for taking too much time to reach the goal state.
Yes, so there's a discount factor being applied, but if the optimal policy is the same and the dynamics is fully deterministic, we would expect everything to be the same. But this is a good indication that the dynamics is not deterministic. There's something sneaky going on this number line, and we don't necessarily know what it is. I'll say later what it is. It's not important now, but just know that typically in oral environments, there are sort of dynamics at play, that even though when you're in a specific state and you take an action, there's then a transition dynamics that is dictating which state you would visit next. So there's some slight differences, but there does seem to be an optimal policy here. Okay, here we're looking at episode length, okay? So on the x-axis we have episodes, same as the previous plot. On the y-axis we have the episode length. So we have these similar dips, seems to go down to a specific number. And then we have this sort of straight line at the top. I don't know if anyone would be keen to interpret why this is the case.
Okay, thank you. So I think after, whatever that is, 3 or 4, the length of the episode, it reaches the optimal in most of these cases pretty fast. And in some of them, it takes a little longer time. And that possibly results in the discount factor giving them slightly lower than 1.
Yes. So what is the optimal episode length here? What is the shortest episode length? Yeah? Okay, so 3, if you just move 1, 2, 3. And then why the straight line at 50 at the top?
I think 50 is the maximum steps that is required.
Exactly. So there's an arbitrary parameter in this environment that means after 50 steps, if you haven't reached the goal yet, that's it for you. That's the end of the episode. Let's see, okay. This is the policy we found. That small, hopefully you can see this. Looks good? Yeah. Looks correct? Right. Cool. Amazing. Okay, see what this looks like. Magic. Steve has now successfully done the number line. Now, this is for, we have 4 states here. This is pretty cool. we have an automated process of finding good policies for this number line. But now we're going to up the ante a bit. Okay? So the original slide I had actually had 10 states. So we're just going to do 10 states here. This is what it looks like. So that's what the slide looked like. Let's sample a policy here. Okay, so now we just have 10 numbers. What's going to happen here with this policy? So again, one is right, left is one is right, minus one is left. The 10 numbers represent the 10 different states, and we always start on the left-hand side. What's going to happen here? Yes, I see the, yes, okay. Same thing, right? So we're going to go down here. Okay. And boom. Right, left, right, left, right, left, right, left. Okay. Okay. So we have the same objective now. We need to help Steve go from left to right. He needs to get his recipe, his strategy. We need to help him get that. Okay. Let's do our good old faithful random policy search. Okay, so we're going to run all of this stuff again. What happened? Yes.
Okay. It didn't meet the goal throughout the episode, so it kept on being stuck, and that's why we have a reward of 0 all through.
Exactly. So in not a single episode did Steve manage to get any return. Let's see here. Oh, episode length. 50s all round. So Steve never managed to reach the goal, ever, in the 100 episodes that we tried. If we sample a policy here, it's going to be, the best policy is just an arbitrary policy. They were all equally bad. This policy, who can tell me, if you look here, who can tell me what's going to happen with this policy? Steve's going to get stuck? Where is he going to get stuck? Is he going to get stuck the same place as last time?
At the third index.
It's going to get stuck at the second state. Exactly. Let's see this. Okay. There we go. So he made it a bit further, but now he's still stuck. Okay. Why is this the case? Why is this so tricky? Well, it's because, okay, there's a number at the bottom there, but anyway, it's very unlikely that you sample the optimal policy through random sampling, because you basically have to get a vector of length 10. All indices should have the number of 1, and the probability is actually like 0.09%. It's very, 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 very low that you just randomly sample that. And we did 100 episodes, so probably not going to get that. So random policy search is cool, but it's definitely not the way to go. We need something that's more intelligent and something that can work better. Okay, so this brings us to this idea of policy gradient. If you think about random policy search, it's like just, shotgun approach, spaghetti against the wall, try and find something that works. But it would be nice if there was some more intelligent way we could search in the space of possible policies and do it intelligently such that we find good working policies. And a great way to do this in any form of optimization is to use gradient information. So if we can calculate some form of gradient, we can follow the gradient signal and get better policies. And this is exactly what the policy gradient method is about. It's saying we'll use this gradient information during policy search to get better policies. And how do we do this? Well, we essentially now, instead of just having this policy that's fixed in the sense of this state you do this action, we actually have a parameterized policy. We have a function that has some parameters, and if we change these parameters, it changes what the policy tells Steve to do. And we're going to have a very simple one. I'll say more about that just now. But this recipe of policy gradient can really be summarized with this line here. So let's say your policy is pi, so it's some function. It depends on some parameters theta. And this is theta sub 0 saying, sub naught, just saying that this is the first iterations of parameters I have. We essentially use this to see how well it is. How well do we do in the environment? And this is captured through this return G, as we've used the whole time. Then if we can calculate a gradient of the return with respect to the parameters of the policy, then we can actually update these parameters to have better returns for the subsequent policy. And so that's what we do. We calculate the gradient, the parameters with respect to the return, and then we just get a new set of parameters. We can keep doing this. Where do we get the gradient from? Well, we get it from something it's called the policy gradient theorem. So we're not going to go through that, but there's some math you can do that shows you if you have the objective of the expected return, you can get a sort of quantity out that's an approximation of the gradient in terms of expectations. But we'll leave that. So our policy here is going to be a tabular policy. So for each position, each state, we're just going to have a simple number. And to get our decision, like to get our policy out, we're going to take this number and send it through a sigmoid function to give us a probability of moving right. Okay. Then what is the algorithm? Well, the algorithm is as follows. You run an episode, you calculate the return for each step, and then you calculate the loss. So here we're talking about loss, but it's actually just, we want to maximize the return, but we just take negative of that objective to make it a loss for optimization purposes. We compute the gradient with respect to the policy parameters. So again, these policy parameters are kind of like the knobs we turn. As we turn them, they change what Steve does, and we're trying to find the best ones. And if we compute the gradient with respect to them, we can follow the gradient, in this case, negative gradient, to find the best value, loss value, which gives us the best parameters for the policy. Best recipe for Steve. Okay, so that's step 3, calculating the loss, and then step 4 is updating the parameters using gradient descent. And we repeat. We just do this. Okay. So here we're just making our policy function, and here is what it kind of looks like. So the parameters at the moment are just a bunch of zeros. Zeros is sort of a good initialization because what it means is if you look at the probability of going right or left with the sigmoid, it'd just be sort of 50-50. So this policy, we have no preference whatsoever. Steve is just randomly moving left or right. Okay. Now we are going to run this policy gradient method, and again, no need to actually look at the code here, but so we do a training run. We're calculating the returns as we go and the loss, and we can see the loss is nicely sort of going down, and the return seems like it's going up. And what did this look like? So here is sort of the training progress. So we started with sort of some return there, and then it's not very stable, but eventually it kind of gets to a set of parameters that seems to give some nice returns. We couldn't do this before, right? Couldn't do this before with random policy search. So if we look at what the probabilities are now for going right, we see they are quite close to 1. And then if we look at the policy that comes out of this, if you were to sort of, basically just round the probability that you do get, looks good. What do you think? You think it's a good policy? It'll do what it needs to do? Yeah, ignore the zero, sorry. I think it's a mistake in the notebook.
So then it's good.
Yeah, it's good. Okay. Just note the something I didn't mention is the goal state it's what's sometimes called an absorbing state. So once you reach the goal state, the action you take in that state has no meaning. So the last number could be left or right. It doesn't matter. From there on, you've reached the goal state. So this is in fact the optimal policy, which is great. Like we can visualize this. We have the 10 states. Go for it. Steve. Nice. Isn't this cool? It's super cool, right? Yeah. Automatically just figures it out. Okay. Okay. Let's go back to the slides just to wrap up. Yeah, question.
I'm inquiring about the guarantees on the convergence, since you're dealing with gradient descent and so on, and how difficult is that to manage, or do you have to deploy all the range of techniques for neural networks to combat that as well, convexity and so on?
Yeah, exactly. I think there are some convergence guarantees in like tabular settings, but like once you have deep neural networks, and depending on sort of the complexity there, like I think there are maybe even some results if you have like multi-layer linear networks, which kind of, linear models and things like that, but like once you have non-linear layers in deep neural networks, I'm not sure. I don't think there are some guarantees. Now that I say it, I think there are actually. There's this whole area of mirror learning that like kind of has done some work with advanced policy gradient methods and to give them some guarantees. So, yeah. I would say there are some results, but the thing about theoretical guarantees is like, even though you have them, it's nice to know when the rubber hits the road in terms of optimization. It's not like, it's like neural networks being a universal approximator. In theory, yes, but like, can you actually optimize to get the arbitrary function you're looking for? And the answer is not always yes. Hope that made sense. Okay. So just to quickly recap, we have Steve. Steve wanted to get all the way from 0 to 1, and our goal was to help Steve. Steve could be in a particular state in this environment, take a particular action, move left or right, and there were some dynamics. We didn't know it at the time, but what the dynamics were is essentially if you said you would go left, you would always go left. If Steve decided to go right, he would go right 95% of the time. 5% of the time, the environment would actually send him the opposite way. So this was running under the hood, but in the real world, we might not always know the dynamics underlying some sort of complex transitions. Then there's this policy, what we said is the recipe. It's sort of like which action to take at a given state. What we want is to find the best possible policy. And then we kind of need some way to optimize to get to the best policy. And here we can specify some rewards. We said 1 at the end, 0 everywhere else. There's this discount factor we can apply to the reward signal, and then compute the return, which is this sum of discounted rewards or discounted sum of rewards. And use this as our kind of signal, our optimization signal. And then something I haven't mentioned before, but essentially if you take all of this together, like states, actions, the dynamics of the environment, reward, and the discount factor, you have essentially the formal kind of setting for sequential decision-making called the Markov decision process. So most of reinforcement learning is kind of operating on top of this idea of being using Markov decision processes and finding solutions to them. And then finally, in terms of like the policy gradient idea, we say we have a set of parameters. For each set of parameters, there's a value of the return if you were to actually run the policy in the environment. So the return is a function of the parameters. For every set of parameters, we might get a certain return when we run this policy in the environment. And we can calculate the gradient with respect to the parameters. And then we can simply, in this case, do hill climbing, or we can optimize in terms of the loss, just take the negative of the objective. And then we keep going up, we update the parameters until we find something that we feel is a good policy. And this, in a nutshell, is the policy gradient method, and also a bit of like a flavor of reinforcement learning, and this as a particular approach. Of course, there's a whole universe of techniques, there's a whole universe of other things. Also, everything goes down into some gnarly theory if you want, but I hope this gives at least the intuition. And yeah, then thanks, and I hope you have happy trainings in your practical sessions. Thank you very much. If there's time, we can take questions. I'm not sure if, if there are any questions.
Okay, so let's say Steve is in a crazier world where he can take different paths, and you want to create an RL agent that can find the shortest path that Steve can take, right? And in that case, you can take any action really. So how does policy gradients, can you just formulate how policy gradients would work in that case, like assigning probabilities to the actions that you can take in any given state?
Yeah, definitely. So in a grid world, maybe you have a bigger action space. You can move up and left, right, down. You can formulate the reward in a similar way. So maybe if you want to reach some goal state within the grid, you can get a reward of 1 in that goal state, 0 everywhere else. And then if you have a discount factor that should sort of incentivize a shortest path solution. And then in terms of like a policy, you can parameterize the policy instead of maybe like binary sigmoid style, perhaps just use like a categorical distribution. So you have, for each possible action, up, down, left, right, there's a probability of taking that action. And across all the actions is summed to 1. So you have this distribution over what you can do. And then your task essentially is to find the policy that at each given state gives you the best distribution of which action to take next. Yeah, I hope that made sense. Okay.
Yeah, thanks a lot for the presentation. Great stuff. I just have a question around the theta, the parameters. What is the intuitive interpretation of those? Because you said it's like a knob, right? In this case, it seems to be the tendency to move right, which also seems to be kind of your policy as well. Is it always the same, or in some complex situations is it different, i.e. your theta and your actual policy? I'm just trying to get a better sense of the delineation between those and just interpretation of them.
Yeah,
thanks.
So in the tabular setting, it can feel a bit confusing because you have, you're basically representing your states as in a table, and you kind of just have these numbers within the table, and they represent your parameters, but also then like very directly translate to the policy you would follow. But if you have a more complicated function, so your policy can be sort of any arbitrary function that maps from a state to like a probability of taking an action, or a distribution over actions, depends which way you want to formulate it. But that function can be very, very complex. It can be like a very deep neural network with thousands of parameters. that's sort of, the parameter side of it that you want to optimize, but it's just essentially creating a mapping from state to action, where this mapping is very direct. Yeah.
Thank you so much for that this tutorial. So please, can you go back to the slide just before now?
This one?
Yes. So we understand that in mathematics that turning point is essentially zero, and it basically, like in neural networks, we try to ensure that we hit the minimum point. That's where convergence is made, right? Now, looking at this graph, does it mean that in reinforcement learning, we try to maximize the return, and that way convergence would be when we hit the maximum point?
Yes, yeah. So maybe it was a bit confusing how I swapped between the two, but typically in code, when you code this up, you are trying to maximize the return, but you will actually just optimize the negative of that objective as a loss function, because just like optimizers, it's easier to kind of just work in terms of a loss function. But here, this is almost like the pure conception, is to say we care about maximizing returns, and so we're actually doing gradient ascent up the function and trying to find the highest hill on the like landscape of parameters as a function, or to return as a function of parameters. Yeah. Yeah, no, excellent question. So in actual fact, when you do this, everything is kind of like probabilistic. So even the objective is framed in terms of like the expected return, and usually the policy gradient is in terms of like an expectation. You're approximating the gradient in expectation. And the whole point there is exactly like your policy itself can be stochastic. So you're sampling from a distribution, so you won't always get the same episode. And indeed, the dynamics could be stochastic. So what you're looking for then is to say, I'm not trying to optimize just given one kind of episode and the return I'm getting. I'm trying to optimize over the expected behavior, like over averages of like hundreds and hundreds of episodes for a given set of parameters. I hope that answers your question. Okay. Yes, sure. So if I understand the question, it's like we have this very simplified setting. We showed how it can solve this simple number line with Steve moving left to right. But where can we actually apply this in the real world? Does it make sense? How complex type of problems can we handle? And really the answer is that if you go here and you have this MDP, which I said is this Markov decision process, that is sort of like a formalism for the decision-making problem that RL deals with. Any problem where you have states, there's something you can define as a state that you visit, and you take a particular action, and that transitions you to a next state, and you have to find the optimal sort of decision-making trajectory. You can apply these ideas. Now, it does get tricky in terms of like, the modeling you'd have to do. Maybe it's very complex underlying dynamics. There's a very complicated function between state and actions that makes sense. But this is an extremely, extremely general recipe. Like, for example, if I go here, for example, ChatGPT, right? Take ChatGPT. So a few years back, the magic ingredient that really launched ChatGPT into a common app is to really have the assistant be useful and understand what humans like and help them. And this was done with reinforcement learning. So there, what is the state? Well, the state is a particular part of the conversation. It is sort of like a prompt, like, hey, can you help me with doing X or Y or something like this? And then what is the action? Well, the action is what the language model can actually do. Like it can decide to assist in certain ways. And then what they did is they got many examples of people rating what they like best between certain replies. So if you think of like how would you reward beauty, or how would you reward something like good poetry? It's very difficult. But what you can do is you can ask people, what is more beautiful? What do you find to be the better poem, A or B? And they did this thousands and thousands of times. And then what they did is they had this language model train on producing what is the most beautiful, the most thing that is the nicest reading poetry. And this was done with policy gradient methods, reinforcement learning. So it takes a while to kind of get your problem into this formalism, understand what the tool is you would like to use, but still it is extremely general. Like lots of, I could go on, like I could really go on with problems, but I hope you get the idea. Yeah.
Thank you for the.
Yes, so that is completely what we're trying to do, right? Like trial and error learning, correct from mistakes. But there are very tricky kind of paradigms within reinforcement learning. So if you think about what's happening here with how we're rewarding Steve, is we're saying, okay, you get a reward of 1 when you reach the goal state, you get a 0 otherwise. There's no information in between. You only get essentially your signal when you reach the end. That is called a sparse reward function. You can have a dense reward function. What would be a dense one? A dense one would be something like give -1 at every step and then 0 at the end. So it means the longer you move right and left, the worse your reward's getting. So you're incentivized to finish quickly, and you will probably get the same behavior. Okay, so maybe you think, oh, that's a good reward function. Why at all would you use the sparse one? Well, sometimes sparse rewards are much easier to kind of codify what you actually want to achieve. So a good example is chess. If you take chess and you have a reward function that says, okay, keep taking opponent pieces. That's what you should do to win. Well, you could actually be in a situation where you could checkmate, but because of this reward signal, you just keep taking random pieces instead of going for the win. So what do? Well, you say, no, this is not actually what we want to optimize. We want to optimize winning. And so the reward is just 1 if you win, 0 if you draw, -1 if you lose, that kind of thing. But then it becomes a much more difficult optimization problem. The reward is very sparse. There could be hundreds of moves before you actually win or lose. And now you need to go back to all of those moves and do what's called credit assignment. You need to somehow know which moves are good, which moves are bad. And all of these things play a role in solving practical problems, like thinking about dense versus sparse rewards, thinking about how aligned does this reward function then, is this reward function actually aligned with what I care about? How difficult does it make the optimization problem? Are there techniques that are very good for sparse reward versus dense reward, and should I rather prioritize them? So these are all things to think about. In terms of the this example, I purposefully made the policy deterministic for sort of like pedagogical purposes, so that Steve would get stuck. Maybe very quickly someone would think, okay, yeah, but a stochastic policy is better to randomly get some signal and not get stuck. And this, again, is a big sort of topic in reinforcement learning, is this idea of how much should you explore? Like, how much is random behavior good to get information, to get signal from the environment, versus doing what's optimal? Because the moment you do something, the moment you sort of hone in on a specific strategy, a specific recipe of how to act, you are disregarding sort of the diversity of possible futures you could see. So very often in RL, there's almost like a curriculum of exploring a lot for a certain phase, and then starting to hone in more and more on what is the better thing to do. Yeah.
We have time for one more question.
Okay,
cool.
One more.
Okay, thank you for the question. I see that sometimes we can use log gradient in policy gradient instead. We can use the log of the policy instead of gradient only. So why and where to use log and where to not use log? And another question is, with an agent with a multitask, how to maximize the return when he has to do tasks that depend on the environment? Yeah.
Okay. So the first question on the log, this typically just comes from the derivation of for example, the gradient of the objective. So often, if you think about, let's say you think about the probability distribution over an entire trajectory, right? You can actually decompose that, like just with probability theory, into these products of marginalized probability distributions, and they multiply with each other, which is nasty. And just taking the log doesn't really like change the objective, but you get a sum instead of like a product. And this typically just makes things easier. And if you keep deriving out, you find your objective that you want to optimize in terms of the log probabilities. Then the second question was how to apply reinforcement learning in complex dynamics situations, I think. Yeah. So there are a few things. So let's say you want to apply RL in the real world, and you don't have full control of what's happening. Let's say you're trying to, something Google tried a few years back is like they had weather balloons. And they had these weather balloons, and they would try and like control like how they floated with RL. Now in that situation, you don't have full knowledge of the dynamics, because the dynamics is literally nature. It is very complex wind, and I mean maybe we're good at predicting nowcasting the weather, but you won't get it absolutely perfectly right. So we don't have full knowledge of what's going on. But what can you do? Okay, there are a few things. You can simulate that. You can build some sort of simulator using physics informed and all the sort of weather modeling you can, and then you train using the simulator, and then you hope that this transfers to the real world. Like after you've trained in simulation, you put this balloon out in the wild, and then hopefully it does its thing okay. The other thing you can do is actually use sort of planning or kind of like something like a world model. So again, you're trying to sort of model what the dynamics around you is doing, and then if you have an accurate enough model, you can essentially simulate the future, see what the dynamics is like, and then kind of use that information for the current state you're in to take the best action you can. So there are various things to deal with complex dynamics, but yeah, it is tricky. Okay, I think we're out of time. Thank you very much. I hope you enjoyed the tutorial, and hope you join the practical sessions.